So for our next presentation, it's jointly developed by Mohamed, Altameemi, and Professor Gustavo Parra Montesinos from University of Wisconsin at Madison. And so, Gustavo, it looks like you're actually doing the presentation. I thought Mohamed, but yeah, so welcome.
Good morning, everyone. Again, my name is Gustavo Parra Montesinos. I'm a professor at the University of Wisconsin-Madison. This is a research that one of my doctoral students is conducting, Mr. Mohamed Altameemi. Unfortunately, he couldn't come to the ACI convention, so I'm in charge of presenting for him. But as you know, students do the very hard work. If not all, most of the credit goes to him for the work done on this project. So what I will be talking about is on a recent experimental study that we've done at Wisconsin on the seismic behavior of coupling beams, but in particular with some relatively newly developed steel fibers, which we call double hook steel fibers. So first, to put things into context, we're talking about coupling beams, so that means we're talking about structural wall systems. Now, in general, when you have structural walls, let's say mid to high-rise buildings for lateral strength and stiffness, well, walls are actually very restrictive in terms of space usage. So typically, we need to have openings for doors and windows. A common trend in the past few decades in the United States is to use what we call core walls around the core of elevators. So you're going to see, as shown in this photo, well, that we need these openings for, in this case, doors, and that leads then to the wall, rather than being solid, being split into several walls connected then by these short and deep members that we call coupling beams. Now, because of the fact that they are short and deep, these members are subjected to very high shear stresses, and also given the geometry of the coupling beams with respect to the couple wall system, they tend to be subjected to very large rotations, much larger than the rotations the whole wall undergoes during a major earthquake. On the other hand, it is beneficial to have these coupling beams because the system being coupled has a much larger lateral strength and stiffness than the summation of the strength and stiffnesses of the walls being separated because of the coupling action provided by these coupling beams. Now, looking into fiber reinforced concrete within the context of this presentation, we're talking about the use of steel fibers which are mixed with the concrete. So they are relatively short fibers, typically 1.2 to 2.5 inches in length, and they are mixed with the concrete. The idea is to have a random distribution of fibers. As you can see in the photo on the right, well, steel fibers typically have deformations to provide for mechanical anchorage with the concrete. Now, normal fibers, let's say this one with a single hook, are designed to slip rather than to yield as a crack opens. So as a crack opens, any fiber bridging that crack will tend to slip. There will be some local yielding at the ends where the hooks are, but along the length, they are not really expected to yield. Now, there are more modern fibers that have more than one hook, so they have multiple bends at the ends, and these fibers then are designed to then not pull out, but rather than yield along the length, and they have to be made with a very high strength steel, and also they have to be a little bit longer to prevent fracture at relatively small crack width. And on the left, we see a photo of fibers being mixed with concrete. We can actually basically mix these fibers in a ready-mixed concrete plant for large-scale operations, and up to 150 to 200 pounds per cubic yard, which are very large dosages of fibers. We have managed to do that in large-scale operations with a good fiber distribution. Now, I'm going to be referring to a particular type of fiber-reinforced concrete. I mean, we have many types of fibers. we can use them in different amounts. So the performance that you can get could vary significantly. So just to lump this into one particular class, I'm going to be talking about what we call high performance fiber reinforced concrete. And the main attribute of these high performance FRCs is the fact that if you take a sample made of this material, no reinforcing bars, just the fiber reinforced concrete, and you subject it to direct tension, you're going to have, after first cracking, what we call a hardening or pseudo-strength hardening response. So we see on the top right figure is a plot of tensile stress versus average tensile strain. And what you see, you have cracking, but then you have this hardening response. And then once you have the capacity of the fibers bridging one particular crack reached, then you're going to enter the softening branch of the response. Most fiber reinforced concretes exhibit a softening response after first cracking, so they don't have this hardening response. Now, one advantage of this hardening response, besides the fact that you have this increase in tensile stress and strain capacity, is that that leads to multiple cracking compared to if you have fiber reinforced concrete without bars, you're going to have a single crack. If you have with reinforcing bars, of course, you have, because of the interaction between the bars and concrete, multiple cracking. But comparing a reinforced concrete member with a high-performance fiber concrete member, you can see that you get a much denser distribution of or network of cracks, which means that you distribute the formations more evenly, so as opposed to just reinforced concrete where you need larger crack width. So basically you have a lot more tolerance to deformation when you're dealing with these sort of materials. Also in compression, these materials behave like well-confined concrete because you have the fibers that are restricting or providing lateral restraint against lateral expansion as the concrete reaches the peak or past the peak stress in compression. So that tells us that, well, maybe we can actually reduce the amount of confinement steel or transfer confinement steel when we use these kind of materials, because we start already with a material that has a lot more deformation capacity in compression than plain concrete. Now, in terms of the ACI 318 provisions for design of coupling beams, well, there are various conditions, but the one that is of interest to us in this particular presentation is this one. When we're dealing with coupling beams which have an aspect ratio or span to depth ratio between 2 and 4, most coupling beams in the United States fall within this category for medium to high-rise buildings designed in the past 20 years or so. Now, if you fall into this category, then you have two options in the ACI code. Either you design the coupling beam with a diagonal reinforcement designed to resist the calculated shear demand, and that comes with very heavy amounts of transverse steel to confine either the diagonal reinforcement cages or the whole coupling beam. Or you use the detailing for a special moment frame beam. Now, if you're dealing with a diagonal reinforced concrete beam, you can design for a shear stress of 10 root of F prime C in PSI. You get 8 root of F prime C if you are dealing with special moment frame beams. Most designers choose to deal with a diagonal reinforced concrete coupling beam because of the higher shear stress. Also, they have or exhibit much better behavior in terms of deformation capacity than a special moment frame beam. Now, as I mentioned a minute ago, well, we need special confinement reinforcement. Is similar to the confinement reinforcement we need for potential yielding regions in a column of a special moment frame. So that actually leads, in combination with the diagonal bars, to severe reinforcement congestion as shown in this photo. So you can get very, very large diameter diagonal bars required to resist the entire shear. Also, the larger the aspect ratio, the shallower the diagonal bars are, and the less efficient they are. So you end up with fairly large areas of diagonal reinforcement. In this particular case, the confinement is provided to the diagonal reinforcement rather than the entire coupling beam. The transfer steel for the coupling beam regions outside of the diagonals, as you can see, is very light. Now, this is a very complicated thing to build, not only because of the diagonal reinforcement cages that intersect in the middle, so they need to, the bars need to be offset, but also you have the transverse steel require, for example, when you're dealing with a special boundary element, which is a fairly closely spaced transverse steel. So you have to thread each bar through the edge or boundary region of the two walls being connected. So this is a very labor-intensive and time-consuming operation. Sometimes these bars are so heavy that you need 2 people and maybe a crane to handle a single bar. So as we can see, these beams behave well, but there is a price you have to pay in the form of the reinforcement congestion, the time associated with the construction of these coupling beams, increasing labor. I'm told by contractors that sometimes the time per floor increases by 1 day if you're dealing with these coupling beams. So you can imagine if you're dealing with a 30, 40-story building, that's quite an increase in construction time. So if you use a material like one of these high-performance fiber concretes, well, maybe we can reduce the transverse steel because the material behaves already like well-confined concrete, but also, well, maybe because of the tensile stress-strain behavior of the material, we can eliminate diagonal bars. And we have shown in the past that that is possible in some cases. We had in the past evaluated 3 types of steel fibers, all 3 hooked, but we call them like single hook because it is just a single hook at the ends. And we've evaluated these fibers in volume fractions between 1 and 1.5%. So all the way to about, so it's between about 130 to 200 pounds per cubic yard. And we've seen that in some cases we can eliminate diagonal reinforcement if we're dealing with aspect ratios, span to depth ratios at least of 2. Now, what we decided to do in this case was to evaluate then these other types of fibers with double hooks with the idea of trying to use lower fiber contents. Also, the larger the fiber in terms of diameter and longer, they are cheaper to be manufactured. So we wanted to see, well, can we come up with a more economical sort of solution? So we tested 12 coupling beams. They were large scale, as I will show, on the large displacement reversals. We look at different aspect ratios ranging between 2 and 3 to cover the typical range of aspect ratios. Shear stresses between 6 and 10. Remember, 10 is the upper limit for a diagonal reinforced concrete coupling beam. This is in terms of square root of FRC in PSI. We targeted a compressive strength for the concrete of 8,000 PSI. And we evaluated 2 types of double hook steel fibers and in 2 dosages. Now, we didn't try all combinations, so we ended up with 3 steel fiber reinforced concrete or SFRC mixtures that were evaluated. This shows the photos of 2 of the 2 fibers evaluated. You can see now you have 2 hooks here, and you have like a 1.5 hook on the other one. So the left one is called a 5D 6560 fiber. The one on the right is a 4D 8060 fiber, both manufactured by Becker. So we evaluated the 5D, the one on the left, at either 1 or 1.25% by volume. The one on the right at 1.25% by volume. Both fibers have the same length, 2.4 inches. Strength, nominal tensile strength for the left, 335 KSI versus 260 KSI for the one on the right. And the diameter for the one on the right is a little bit smaller. So the aspect ratio is larger for the 4D versus the 5D fibers. I don't mean for you to read these. These are the 12 specimens. They don't follow a particular order because I lumped them into aspect ratios. So that's why we start with 3, 4, 5. Those are aspect ratios of 2. So we have 2, 25, and 3. Fiber type, different types of volume fractions, and shear stress between 6. Most of them were targeted at 8 root of FRC and some at 10 root of FRC. I'm just going to focus on 4 coupling beams in the interest of time. The interesting thing is the reinforcement detailing. We tried 2 design schemes in terms of reinforcement. because these are made of fiber concrete, and typically the walls are made of reinforced concrete, regular concrete. So we're going to have a cold joint, either because we put some sort of mesh or so to block the fiber concrete to go into the wall if we do cast in place, or because we precast the coupling beams. In the lab, we prefabricated the coupling beams. So what you see is the fiber concrete part, the bars stick out, but we evaluated first the use of these U-shaped dowels to increase the shear transfer capacity at the interface. We expect very large rotations at the interface, so we were concerned about having a sliding shear failure that would occur prematurely. And then towards the end of the testing program, we evaluated a similar detail, but without the U-shaped bars, but making sure we have enough longitudinal steel to achieve or provide sufficient shear transfer through shear friction at the interface. So when I say with U-dowels, that means the detailing at the top. If I say without U-dowels, that means the detailing at the bottom. So I'm focusing on these 4 coupling beams, 2 aspect ratios, 2.25 and 3. For each aspect ratio, I'm looking at without dowels and with dowels. Target shear stress, in most cases, 8 root of 8 prime C. In one of the coupling beams here, we have 10 root of 8 prime C. And volume fraction, 3 out of 4, 125% versus 1%. Just mentioned that we prefabricated these, so we started with the reinforcement cage. Then we cast the fiber concrete for the coupling beam. Then we put it in place. We have 2 massive, very large stiff blocks simulating the edges of the walls, the wall being connected. Then we cast the regular concrete for the walls. The way we tested this, for convenience, we rotated the specimen 90 degrees, so the coupling beam, instead of being horizontal, it was vertical, as you can see here. Now, what we wanted to do, or we needed to do, was to make sure the 2 walls being coupled, in this case, these 2 horizontal blocks, were fairly parallel, or almost parallel during the entire loading regime. So we have these steel links that ensure that the 2 blocks were basically parallel. We applied lateral displacements at the top horizontally, back and forth. And drift, that means the relative displacement of the top of the coupling beam versus the bottom. If I talk about drift ratio, that would be the relative displacement divided by the total coupling beam length. One important thing is that these links also provided some degree of actual restraint, which will occur in a real building, because you have the walls that provide some restraint against the coupling beam expansion, and also the floor slabs. And at the bottom, I'm showing a photo of the specimens of the coupling beam with the 2 blocks and the hydraulic actuator to provide lateral displacement. We had 2 loading protocols. So for most coupling beams, we had 1 cycle at each drift level. We started with basically 0.25%, and then increased 0.5%, 1%, so on, until failure. And then for the last few specimens, we did 2 cycles at each drift level to evaluate the effect of repeated cycles at each drift, and basically stiffness and strength retention during repeated cycles. We also did some material tests to evaluate the performance of the materials. One of those tests was a direct tension test of notch specimens. Of interest here, this is the tensile stress versus crack width obtained for these prisms under direct tension, which were notched. This is normalized by square root of A prime C. And what you can see here is 2 out of the 3 mixes, the ones with 1.25% volume fraction, they had a peak tensile stress after first cracking that was greater than the first cracking stress. So this is kind of the condition for string hardening or a high performance fiber reinforced concrete. We also conducted ASTM 1609 tests. We have also a hardening response for these tests after first cracking. And this is normalized by the first cracking strength. So in some cases, we reach post-peak stress, almost 40% the first cracking stress. Looking into the hysteresis, this is normalized shear stress versus drift response. Well, as you can see, if you pay attention to the y-axis, this is shear stresses over A root of F prime C. Drift at 20% strength decay. Well, in this case, in the negative direction, it went all the way to 8%. For the other pair of specimens, a similar behavior. One had lower shear stresses than the other one. An important thing here is that, red and blue, one with dowels, one without, black and blue, one with dowels, one without dowels, a very similar behavior in terms of drift capacity. So that means that we can simplify the reinforcement, remove the dowels, and still achieve good performance. Summary of the test results, we can get a fairly stable hysteresis response at high shear stresses for all the tests that range between 7.1 and 10.8 root of F prime C. Because of the actual restraint, we got actual compressive forces developed in the coupling beams that were on average about 10% of the product of F prime C times the gross area. We got at least 5% drift ratio before we got 20% strength decay. And the behavior was dominated by flexure until the very end where, for the case of the U-dowels, the coupling beam started having quite a bit of sliding at this section at the end of the U-dowels. So photos showing the damage progress up to 4% drift in this case. As you can see, beyond 2%, pretty much all the cracking had developed. As I mentioned earlier, because of the material we use, we got a fairly dense cracking distribution. And at the end, at larger drift, what we had was quite a bit of damage at both ends of the coupling beam. In terms of effective stiffness at first yield that you can use for an elastic analysis, well, we don't have diagonal reinforcement here, so our effective stiffness are about 2/3 on average of the effective stiffness recommended in Appendix A of the ACI code. Energy dissipation is similar to that of well-detailed diagonal reinforced coupling beams. Whether you had dowels or not, it didn't matter. This is actually a normalized energy dissipation, so basically normalized by an equivalent elastoplastic system. So you get values roughly about 40%, except for this red specimen. This one had the lower shear stresses out of the four I mentioned. So you get quite a bit of energy dissipation capacity, over 20% higher than for the other three. Before I conclude, I wanted to show these two plots. This is basically tensile strength measured in the transverse steel along the length of the beam. So what we have here horizontally is the location. So you have the left end of the coupling beam, the right end of the coupling beam, and then the midspan region. At the ends is where you have more confinement reinforcement. In the middle, you don't have any special type of transverse steel. In the y-axis, what we have is a normalized strain, normalized by the yield strength of the transverse steel. In all cases, that ratio was less than 1. So that means all the transverse steel remain elastic, even in the plastic hinge regions. I should mention that for the middle portion, we were able to count on 4 square root of F prime C in PSI of contribution of the fiber reinforced concrete. So typically, in beams of special moment frames, we use 0 for VC. So we use 4 root of F prime C, so that means we didn't need as many hoops in the middle region, and still with that, we didn't have any yielding. So just to conclude, well, I've shown that if we use a strain hardening fiber reinforced concrete in coupling beams with aspect ratio of at least 2, we can achieve a stable hysteresis dominated by flexural deformations, even for cases of coupling beams subjected to shear stresses as high as 10 root of F prime C megapascals. We achieved a drift of at least 5% before we got a 20% strength decay. We only needed column type confinement reinforcement at the ends rather than over the entire coupling beam as you require for diagonal reinforced coupling beams. As I just mentioned, we can rely on a contribution of the fiber concrete to shear, the so-called V sub C term, for use in the middle regions of the coupling beam was 4 root of F prime C. And whether you have U doubles or not at the ends, it seems that that did not lead to any meaningful difference in behavior. So as long as you have enough longitudinal steel crossing the interface, or the beam ends or the beam wall interface, to have enough shear friction, you should be fine in terms of not having any sort of sliding failure prematurely. With this, I conclude. I want to thank Becker Corporation for providing financial support for this research, as well as the University of Wisconsin-Madison. Thank you.